Hariom. Now we have obtained the formula for position vector of center of mass as RCM equal to M1 R1 plus M2 R2 divided by M1 plus M2. Okay. Now suppose that we consider the mass M1 equal to M2. Let it be equal to M. I mean both the masses M1 and M2 are equal, and let it be M. Then if I substitute that condition over here, you will be getting RCM will be equal to M R1 plus M R2 divided by 2M. And finally, RCM will be equal to R1 plus R2 by 2. So what this equation tells you is that when the two masses are equal, then the position vector of center of mass will be falling exactly at the average point of R1 and R2. That means exactly in the middle of the line joining the two particles. So center of mass will be exactly in the middle of the line joining the two particles when the two masses are equal. Another case is that suppose M1 is very large compared to M2. Second case, if M1 is very large compared to M2, that means M2 is negligibly small. So when I apply the case over there, you will be getting the equation as from here RCM will be equal to M1 R1 plus M2 R2 divided by M1 plus M2. But M2 is negligibly small, and therefore I can have this RCM almost equal to M1 R1 divided by M1, or RCM will be almost equal to R1 itself. So what this result tells you is that position vector of center of mass is almost equal to position vector of M1. That means that the position of the center of mass will be very close to M1. Position of the center of mass will be very close to M1. That means the center of mass point will be close to the larger mass of the two particle system. So if the two masses are equal, the center of mass will be falling exactly in the middle of the line joining the two particles. But when one mass is very large, then the center of mass is found to be falling very close to that larger mass of the system. So this is a very, very important point to be noted. If you are given a distribution of mass, then asked to find the center of mass or asked to assume the center of mass, you can very well say the center of mass will be falling near to the larger mass of the distribution. It's a very important result you can obtain from. Okay? Then let us assume an example for finding the center of mass of a mass distribution. A mass distribution we are taking and finding the center of mass of that. So let us see the case, that is coordinate system, for example, and I have four masses there, 1, 2, 3 and 4. And it's like this. It is actually a square form. Let us say the side lengths are L, L, L and L. Suppose a distribution like this is given, and if the masses are identical, suppose M, 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 and this also M. Okay? So identical masses, and they are distributed just like four corners of the square. Then where its center of mass will be, or obtain the position vector of center of mass. Then you can go mathematical, or the simple method is that being the distribution regular and the masses are identical, you can just draw the diagonal for this square, and the diagonal meeting point gives you the position of the center of mass. So this is the position of the center of mass term. And if this length is L, side length is all L, then the position will be coming as L by 2 and L by 2. Okay? This is one way of finding the center of mass of a given mass distribution. If the distribution is regular and also the mass is identical, then this method can be adopted. Otherwise, you will be taking the position of each particle and then substituting in the equation x is equal to m1 x1 plus m2 x2 plus m3 x3 divided by something like that. You will be going according to that. So all these are the points to be noted for the center of mass case. Okay.